So one good way to learn about recursion is by doodling these patterns called fractals that are self-similar. One of them is called Sierpinski's triangle. So you got big equilateral triangle on your page. Sierpinski's triangle is a fractal. Fractals are self-similar in that they follow a repeated pattern. Triangles are important in three-dimensional computer graphics in that surfaces to be displayed must be broken into triangles. Recursive subdivision of triangles is one way to generate high-resolution graphics. I know there's a lot of words there. Don't worry too much about it. Here's how you do Sierpinski's triangle. On an upward-pointing equilateral triangle like the one you see here, find the midpoint of each side and connect them. So I'm going to do this with you because I love doing this. Here, let me see here. Let me get, hit me with the red, okay? So I'm going to find the midpoint of each side. You don't have to be absolutely 100% accurate, but just kind of estimate there. That looks about midpoint-ish. And then it says to connect them. So I'm going to, it doesn't have to be straight edge. You don't have to get out your ruler or anything like that. This isn't, don't tell Miss Koppelman or whoever's teaching the art stuff. There we go. Okay. And so you're saying, oh, Zelda, yeah, whatever. Okay. So then you repeat this process on any newly created upward pointing triangles. So I see that this now is a upward pointing triangle, so I'm going to do the same thing here. Now you don't have to change colors like I did. I'm just trying to demonstrate what's going on here. So there's a newly upward pointing triangle. Oh my gosh, that created 3 more upward pointing triangles. Are you for real, brother? Do you believe that it created 3 more upward pointing triangles? Now, eventually, you kind of have to have a stopping point because you go, okay, I can't draw them any smaller here, brother. But maybe this will be my stopping point here. But then I got to go back to all the other triangles that were that size. Yeah. Got to get this guy too. And then this guy has some of these dudes. I know, you're thinking, isn't this ridiculous? Oh, well, you never thought you'd get to doodle in computer science class here. Okay. Oh, baby. Oh, baby. That's that one. Then I got to go back to these guys. This dude here. Why do I hear mouses clicking? Are you guys done with your Sierpinski's triangle like I am? You don't have MS Paint. Why are you talking? You have a sheet of paper. Here we go. Oh, baby. Oh. Do you guys ever doodle like when you're on the phone? You guys don't even use the phone, do you? When you're TikToking? One of my tennis lessons yesterday told me their mom could hit the Renegade, and I was done. It was end of lesson. That was the beginning and the end of that conversation. I couldn't even look the mom in the eye. I don't even really know what it all means. If you don't think I'm going to do the bottom left and bottom right triangles, you're severely mistaken. Don't think I've forgotten about them, because that's just not true. You can't believe what you read. See, now you could do this on TikTok. You can hit the Sierpinski. Let's see here. I got to hit. Oh, Judas, that was not my best work. Hold on. Now, could you go smaller? Yes. You could definitely go smaller. You ever seen Ian Spital's handwriting? You can definitely go smaller. No offense to Ian, it's very neat and organized. Oh, baby. Now I got to do my green triangles. Oh, isn't it just so satisfying? No! Whoever said no, get out. Screenshot. You can actually make fractals in Microsoft Paint. I've seen it done before. Not that you would want to. Ah. Da 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 da. Gets a little messy down here. I'll admit my hand is just getting tired at this point. But you know what they say? Champions don't cut corners. 1, 2, 3, 4. Oh baby. 5, 6, 7, 8, 9. I've got a couple to go here. About 45. My hand is literally cramping right now. $20 to go. 1, 2, 3, 4, 5. Why? Yeah. Why wouldn't I? 6. No, I'm just kidding. 7, 8. I'm a quitter. 9, 10, 11, 12, 13, 14. I miscalculated. 15, 16, 17, 18, 19, 20, 21. Oh baby. Now, Zelda would be a lot cooler if they had that Sierpinski's triangle instead of the Triforce, I think. But so that's called a fractal. It's a self-similar shape. It's a shape that repeats in smaller and smaller and smaller sizes. There's all kinds of different fractals. You think that's the only one? No. You can do so many. There's one called a box fractal. I'll just show you the beginning of a box fractal. Here's what you do. You draw a box, and then on each one of the corners, you draw a box. I'm just going to do like 3 levels. Just stop whining. It's a beautiful pattern. Why are we whining? Here we go. And then on each one of the corners, you draw a box. That's called a box fractal. I did, and then I erased it, and it brought great shame to me and my family. Yes, I did have it on the whiteboard at one point. That's called a box fractal right there. It's, again, a self-similar shape, a pattern that repeats in smaller and smaller chunks. That's a box fractal there. There's something called a T fractal. If you make a big old T, and then on the endpoints you make a big old T, or a littler T. And then on the endpoints you make a smaller T. That's a T tree or a T fractal. There's all different kinds of self-similar little doodles and stuff that you can do here. And these are all recursive shapes. So there's all different kinds of little recursive kind of fractals you can do. And And these are recursive because they're self-similar. It's the same pattern over and over again on top of itself, and you're breaking it down in smaller and smaller chunks. But you do have to have a stopping point at some point. If you don't have a stopping point, you're going to be here until the end of time just drawing your Sierpinski's triangle or your T-tree or your box fractal. So at some point you go, okay, I'm going to stop when I can't draw a triangle any smaller, or I'm going to stop when my T's are less than 1 inch big, or I'm going to stop when my boxes are smaller than 1 millimeter on each side or something like that. So you do have to have a stopping point. If you don't have a stopping point, you're just going to be doing it forever. Now, if you transfer this to computer graphics, imagine you're telling a computer to draw Sierpinski's triangle. At some point, you have to tell the computer to stop, or what's going to happen? It's just going to keep going forever and ever and ever and locked into the same process. So these are recursive kinds of doodles. There's tons and tons and tons of them out there. You want to see one more, or are you ready to move on? One more? Okay, last one. There's the triangle. So if you draw, like, it's similar to Sierpinski's triangle, but a little bit different. If you draw like an equilateral triangle, and then on each side you draw another equilateral triangle. Oh, that was good. Let me just try this guy again. And then on each side you draw an equilateral triangle. So that's another little type of fractal, and you could obviously keep going. If I started bigger, I could probably keep going for a longer time there. But those are all just different types of fractals, which are self-similar little doodles here. And the reason we're doing them is because it's a good way to start talking about recursion, because they're also recursive. You're doing the same process over and over again until you find your stopping point. So, recursive methods. Similar to Sierpinski's triangle, the steps up here where we did one thing and then we keep repeating the process until we find our stopping point. A recursive method is one that follows two rules. First of all, a recursive method must have at least one call to the same method. In other words, the method must call itself. So I think we actually ran into that. I was kind of demonstrating it a little bit when we were doing the overriding the two-string method in the last unit, and I didn't say super.toString, I just said two-string, and then the two-string method called itself, and the two-string method called itself, and the two-string method called itself, and so on and so forth. So you must have at least one call to the method itself. So if you have a method called M1, then inside of method M1, M1 calls M1, and then M1 calls M1, and M1 calls M1, and so on and so forth. So that's the first criteria. To be recursive, a method must call itself. That's like Sierpinski's triangle. It's self-similar. After you draw the triangle, then you have more upward pointing triangles, and you have to draw more triangles. So first, it's self-similar. It calls itself. And then second of all, you must have a way to stop the recursion. And so this is called, so you have to have a way to stop the recursion, which is called the base case. In other words, a stopping point. Without a base case, infinite recursion happens, which is very bad. Infinite recursion is similar to an infinite loop. You have no way out. Actually, I would say it's maybe even worse than an infinite loop. With infinite recursion, your program is going to crash and run out of memory. At least with an infinite loop, it might just keep going forever and ever doing something. But with infinite recursion, you're going to run out of your computer's memory and crash. So a base case is just kind of a way to tell you a way to stop. Like what was our base case for Sierpinski's triangle? I got tired. Keep drawing triangles till you get tired, or keep drawing triangles until they're too small to draw anymore. That would be your base case. Wait, what do you mean? I can zoom in. No. Okay, never mind. Okay. So those are the two requirements for something to be recursive. You have to have at least one call to the same method, and you have to have a way to stop the recursion. So The most basic example that people usually start with when they're learning about recursion. Oh, why are we learning recursion? Because it's on the AP test. And it's a good way to write programs that's maybe a little bit simpler in some ways than writing a loop, sometimes. We'll talk about that more, but we're learning about it because it is on the AP test. You have to be able to evaluate recursive methods. The College Board decided that. So a good place to start is by computing factorials. You guys know what factorials are, but I do have an example here if you've forgotten. 3 factorial, that's what this exclamation point means. It's not just 3, it's 3 factorial. 3 factorial means you do 3 times 2 factorial. What's 2 factorial? Well, then you do 3 times 2 times 1 factorial. What's 1 factorial? Well, you do 3 times 2 times 1 times 0 factorial. And 0 factorial is my base case. I stop when I get to 0 factorial because I know that's just defined as 1 in math. So here's how you can define factorial. You can say any number n factorial is n times n minus 1 factorial. N times n minus 1 factorial. This is our recursive call, essentially. I should do that in blue. Hold on. Let me just try this again in blue. Where are you? There we go. N times n minus 1 factorial. That's our recursive call. We're saying factorial is going to call factorial. N factorial is the same as n times n minus 1 factorial. And then our base case is when we get to 0 factorial. When you hit 0 factorial, you're done. It's just 1. And then you go back through. So as an example, 3 factorial is defined as 3 times 2 factorial. What's 2 factorial? It's 2 times 1 factorial. What's 1 factorial? Well, it's 1 times 0 factorial. And then that's when I finally hit my base case. 0 factorial is 1, and that's when I'm done. And so I do 3 times 2 times 1, which is 6. The method knows how to solve the base case. We know that 0 factorial is just 1. If you call the method with n is greater than 0, it reduces the problem into a subproblem for computing the factorial of n minus 1. The subproblem is simpler and smaller. How do you build a house? You put down a brick and then you build the house. How do you build a house? You put down another brick and then you build the house. How do you build the house? You put down another brick and then you build the house. It's the problem is getting simpler and simpler and simpler until, how do you build a house? You got 1 brick left, you put the brick down, and then you're done. It's that simple. How do you get through your school day? You do first hour and then you do the rest of the day. How do you do your school day? Well, then you do second hour and then the rest of your day. And then eventually you're all done. You're breaking the problem into simpler and smaller chunks. That's what you're doing when you're thinking recursively. What's n factorial? It's just n times n minus 1 factorial, and so on and so forth. So you're breaking the problem down into simpler and smaller chunks. How do we do Sierpinski's triangle? Well, you just draw a triangle at the midpoints. And you just do it again. And you do it again. And you do it again until it's simpler and smaller. A recursive call, meaning the method calling itself. I'm on the back here. A recursive call, the method calling itself. Can result in many more recursive calls because the method keeps on dividing a subproblem into new subproblems. For a recursive method to terminate, the problem must eventually be reduced to a base case. If you are not working towards your base case, you are going to be in an infinitely recursing situation. It's just like a for loop. If you don't have a step expression that works your way to the condition being false, you're going to keep going on and on and on forever and ever and ever. You need to be working your way to the base case. In factorial, when I do n times n minus 1 factorial, n minus 1 is working its way down to 0. So that is working its way towards the base case, so I'll be guaranteed I don't have infinite recursion. When the base case is reached, the method returns a result to its caller. When the base case is reached, the method returns a result to its caller. And when I say caller, I'm talking about the method that called it. The caller then performs a computation and returns the result to its own caller. and so on, and so on, and so on. You guys ever read that one Cat in the Hat book? It's like the Cat in the Hat comes back, where inside of his hat he had like two little helpers. Yeah, thing one, thing two, and then thing one and thing two had like two little helpers, and then they kept having more helpers to clean up all the pink gunk on the walls. Does anybody know what I'm talking about? Some of you, okay. So that's kind of the same thing. You keep going, and then when the job is done, then the little mini thing one and thing two get back in thing one and thing two, and then thing one and thing two get back in thing one and thing two, and then so on and so forth until they're back in a Dr. Seuss or Cat in the Hat's hat, and you're done. Yeah, Ian.
So when you call a recursive method, will it go all the way down and then all the way back up? Before it doesn't go like this.
You're right. It keeps calling and calling and calling and calling and calling and calling until it hits the base case, and then it like zips back up. Sometimes I think of it like a zipper. It like unzips, it does all the jobs, and then it zips back up at the very end. So yes, you're exactly right. So here is n factorial written as a recursive method. Now this is a little tricky here to follow. So I did make the method static, so we didn't need to create any objects. I just called it fact. I hope that's okay with you. Obviously, I couldn't call it exclamation point because that would be an illegal method name. And so I say if the number n is 0, that's our base case. Return 1. 0 factorial is just 1. Then the recursive call is basically saying otherwise return n times n minus 1 factorial. That's what this here is saying. How do I know it's the recursive call? Well, look right here. The name of the method is fact. I'm calling fact from inside of fact. Fact is calling fact. Factorial is calling itself, essentially. So that's the recursive call. And I can tell this up here is the base case because it's not calling itself. It just stops. It just returns some number at some point. So the recursive call is when the method calls itself. The base case is when the method just returns a value and just stops calling itself, essentially. Stop doing factorial. Just return a 1 or something like that. So, we got to talk about how this works here. If I do factorial of 3, let's think about what happens here. If I say call factorial of 3, this 3 will be sent in for n. Essentially, n will be starting at 3. So it goes through, it goes, is 3 equal to 0? No. So otherwise, return n, which is 3 times factorial of 3 minus 1. Factorial of 3 minus 1, which is 2. That method then freezes. It's like in stasis. Have you ever seen, maybe you've seen that movie like Passengers with, what's the girl, Jennifer Lawrence and Chris Pratt, where they're like frozen in stasis and then they accidentally wake up and it's like really creepy kind of a cool movie, but also really creepy. This fact 3 is in stasis. Why is it stopped? Well, it doesn't know what fact 2 is. So how's it going to figure out what fact 2 is? It calls the method again, and now it does its job with fact 2. So n becomes 2 in fact 2. Is 2 equal to 0? Nah. Then it's going to return 2 times fact of n minus 1. Well, if n is 2 now, it's going to return 2 times fact of 1. Remember, fact is just short for factorial here. Then this method is in stasis. Fact of 3 is in stasis because it doesn't know what fact 2 is. Fact 2 is in stasis because it doesn't know what fact 1 is. Okay. Well, what's fact of 1? Let's see. N becomes 1. Is 1 equal to 0? No. Otherwise, return 1, or n, times fact of n minus 1. Now, I know what some of you are saying. Mr. Foster, couldn't you just say 1 factorial is 1? 0 factorial is 1. And now fact of 1 is frozen in stasis too because it doesn't know what fact of 0 is. Then we call fact again and we send it 0. Is 0 equal to 0? Yes. So then it returns 1. Now this method is done We know fact of 0 is 1. 1 times 1. Now it's zipping back up, Ian. 1 times 1 is 1. We know fact of 1 is 1. So this method is done. What's fact of 1? It's 1. 2 times 1 is 2. We know fact of 2 now is 2. Fact of 2 is 2. If you don't see where these numbers are coming from, I'm just going boom, boom, boom. 3 times 2 is 6. And that is my result. Sorry, just zooming out a little bit so we can get the whole picture there. Now, you probably never thought of factorial like that, but it can definitely be written like that. Let's try factorial of 4 together. Now, I have a very specific system for evaluating recursive methods called the box method. I've found that it works. If you don't like it, that's great. I also like the box method because it shows what's actually happening in Java's memory, in the computer's memory. This is called the stack. Essentially, fact of 3 gets called, fact of 2 gets called, fact of 1 gets called, fact of 0 gets called. They just keep getting stacked on top of each other in memory until you find a return value, a base case, and then they pop off the stack until you get back down to the main method or whatever called it. So let's try factorial of 4. I'll show you the box method in all of its glory. Okay, where's my pen? There we go. We'll do this and then we'll take a short break. Fact of 4, well, let's see here. Why do I have black? There we go, okay. Fact of 4, let me look at my method up here. N is 4. Is 4 equal to 0? No. Okay, so I'm going to say, why is that a box? Hold up. Let me try drawing. There we go. Fact of 4. So I call fact of 4. 4 is not equal to 0, so it's going to be returning 4 times fact of 3. What's fact of 3? I got to find out. So then I pop one more thing on, or I push one thing onto the stack here. What's fact of 3? Well, 3 is not equal to 0, so it's going to return 3 times fact of 2. What's fact of 2? I do not know. The computer doesn't know. It only knows what fact of 0 is, so then it's going to do 2 times fact of 1. What's fact of 1? I don't know. The computer doesn't know. It's not the base case. Fact of 1 is 1 equal to 0? Nah. So it's going to return 1 times fact of 0. What's fact of 0? Oh, I left just enough room. Let's go. Fact of 0? 0. N is equal to 0. So now I get to start popping stuff off the stack. That's just going to return 1. Fact of 0 is 1. 1 times 1, that's 1. This comes down here. Fact of 1, I know now to be 1. 2 times 1 is 2. I pop that off the stack. I know fact of 2 now is 2. 3 times 2 is 6. I pop that off the stack. Fact of 3 is 6. 4 times 6 is 24, and that is my answer. Factorial of 4 is 24. Questions on that method so far? Identifying and tracing recursion, like I just showed you, is on the AP test. Are they going to say, here's a recursive method to trace? No. What they're going to do is give you some code that looks like this and say, what's fact of 3? Whose job is it to identify that it's recursion? Your job. How are you going to know that it's recursion?
The method is inside the method.
The method is calling itself. Very good. The method's inside the method. All right, let's take our 2-minute break here. Let's go stretch our legs, get a drink of water, and we'll be back. Check your phone if you need. There are tools to kind of help you visualize recursion. One of them's this Java tutor, which sometimes gets linked on the CS Awesome site. This other one's Jelliet, which is kind of a download. When you click on it, I think it tells you, it's an unsafe website or something. Then you can just click advanced and keep going. Right, Nishan? We did that earlier. You can just ignore it. It says not secure, whatever. I don't care. But here's what Jelliet looks like. And I did put in... I put in factorial here. What should I do factorial of? Factorial of 10? Here, I'll do it really quick. Factorial of 10. This is a tool called Jelliet, and it kind of shows you what's going on. I'm going to start it slow, and then I'll speed it up here for you. So main calls fact of 10. N becomes 10. Is 10 equal to 0? No, 10. And you can see on the left side, it's tracing it too. So fact of 10 is going to be 10 times fact of 9, and then it calls fact of 9, and it goes, okay, n is 9. Is 9 equal to 0? Now I'll speed it up so it goes a little faster here. And it goes, 9 is not equal to 0, so let's call fact of 8. Is 8 equal to 0? No, it's not. So then let's do 8 times fact of 7. Is 7 equal to 0? No. So then we're going to do 7 times fact of 6. Is 6 equal to 0? No. So then we're going to do 6 times fact of 5. Is 5 equal to 0? No, it's not. So then we're going to do 5 times 4 factorial. Is 4 equal to 0? No, it's not. So then we're going to do 4 times 3 factorial. Is 3 equal to 0? No, it's not. So we're going to do 3 times 2 factorial. Is 2 equal to 0? No, it's not. So we're going to do 2 times 1 factorial. Is 1 equal to 0? No, it's not. So we're going to do 1 times 0 factorial. 0 equal to 0? Yes, it is. So we return 1. Then we do 1 times 1, which is 1. Then we do 2 times 1, which is 2. We do 3 times 2, which is 6. We do 4 times 6, which is 24. We do 5 times 24, which is 120. We do 6 times 120, which is 720. We do 7 times 720, which is 5040. We do 8 times 5040, which is 40,000. We do 9 times 50,000. We do 10,000. And then that's your result. And now they drew their stack kind of reverse. Oh, thank you. No applause necessary. Thank you. I do it for the fans though. And this is kind of the whole trace here. Fact of 0 returned 1. Fact of 1 returned 1. Fact of 2 returned 2. Fact of 3 returned 6. Fact of 4 returned 24. 5 times 24 is 120. 6 times 120 is 720. 7 times 5,004, blah, 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 all the way up until you get the result of fact of 10. So this is just kind of a tool to help you visualize what's going on with recursion. You saw that the methods kept stacking on top of each other until you found the base case, and then once you found the base case, they start popping off the stack until you get down to the bottom of the stack and you find your answer. Does that kind of make sense? Okay, and it is a tool you can download if you want to kind of check it out at home if you're, struggling on recursion. Another type of recursive thing that shows up in your when you're doing recursion is the Fibonacci numbers. Have you guys ever heard of the Fibonacci numbers?
Oh yeah.
Okay, so yeah, some of you have heard of the Fibonacci numbers. It's like you take a number and I'll kind of demonstrate. So like a Fibonacci number is found by adding up the two numbers before it. The sequence starts with 0, 1. So if I go 0, 1, the next number in the sequence is 0 plus 1, which is 1. The next number in the sequence is 1 plus 1, which is 2. Next number in the sequence is 1 plus 2, which is 3. Next number is 2 plus 3, which is 5. Next number is 3 plus 5 is 8. 5 plus 8 is 13. Don't they say these numbers like show up in nature or something like that? I think so. Fibonacci numbers in nature. So yeah, there's like cones, rabbits, flowers. I don't know how it all works. Succulents. Who knows? Yeah, there's all kinds of stuff here. How are Fibonacci numbers expressed in nature? In 1202, the Italian mathematician Leonardo Pisano, also known as Fibonacci, the son of Bonacci. All right, they're hitting me with the slideshow, sorry. I don't know. They got the golden ratio going on here. There's all kinds of stuff. Seed heads, pine cones, fruits, and vegetables. Look at the array. Okay, so Fibonacci number shows up apparently all over the place in nature, but it can be defined recursively. So, here's a method. Let's say this shows up on the AP test. It's going to say evaluate fib of 4. And you're going to look at it and you're going to go, Okay. How are you going to determine that it's recursive? You're going to see that inside of fib, there is a call to fib. In fact, there's 2 calls to fib inside of fib. All right, so let's see what happens here. It says, first of all, number 1, underline the base cases and the recursive calls. I'm going to do my base cases in blue. Base case is where it just returns a value. Here's my 2 base cases. If n equals 0, return 0. How do I know it's a base case? Because it stops calling itself. And then here's my other base case. Else if n equals 1, return 1. Those are my 2 base cases because the method is not calling itself. The recursive calls. This is how you would realize on the AP test that it's a recursive question. I'll do my recursive calls in red. Here's where I see it calling itself. Fib of n minus 1 and fib of n minus 2. Now, you won't be asked to underline them on the AP test, but this is what you should at least be doing with your brain to realize this is a recursive method. How do I know? Because it's calling itself. How do I know when to stop? Because I can recognize the base cases, the places where it just returns a value. So, draw and evaluate the stack for fib of 4. All right. Now, this is a little bit tricky because it's got 2 recursive calls. I'm going to give myself plenty of room here. Basically, we're trying to figure out the 4th Fibonacci number, which is 0, 1, 2, 3. It should be 3, hopefully, if we do everything right. We'll see. So, fib of 4. I'm going to draw this stack, again, a little bit differently because it's got 2 recursive calls going on. All right, when I call fib of 4, imagine that this box is this whole method when n is 4. Does that make sense? So this box here is like a call to fib when n is 4. So I go through. Is 4 equal to 0? No. Is 4 equal to 1? No. So I'm going to return fib of, what's n right now? 4. So I'm going to return fib of 4 minus 1, which is 3, plus fib of n minus 2. Since n is 4, that's going to be fib of 2. 4 minus 2 is 2. Now, since there's 2 recursive calls going on, I'm going to kind of branch here. I'm going to do fib of 3 over here. Leave yourself plenty of room if you can. And I'm going to do fib of 2 over here. Because I don't know what either one of those are yet. Now, again, imagine fib of 4 is currently in stasis. It's like Chris Pratt trapped in the ice box, whatever. And then fib of 3 and fib of 2 are currently active. Well, technically only one of them is going to be active at a time. You can only breathe life into one of these methods at a time. So let's do fib of 3 first, since that one got called first. Fib of 3. Imagine a new box is made for fib of 3 when n is 3. 3 is not equal to 0. 3 is not equal to 1. So fib of 3 is going to be fib of 2 plus fib of 1. Do you guys want me to do this how it really works in the computer's memory? Or do you want me to like demonstrate it where it's maybe making sense more visually? I'll do it like it's in the... So technically in the computer's memory, I would not do this fib of 2 yet. I would just keep going with this left side until I'm done. So what I would do next is I would do fib of 2. I'm going to do it over here to give myself plenty of space. What's fib of 2? Well, fib of 2... 2 is not equal to 0. 2 is not equal to 1. So fib of 2 is going to be fib of 2 minus 1, which is 1, plus fib of 0. And then technically I would just do fib of 1 now. What's fib of 1? 1 is not equal to 0. 1 is equal to 1. So this is just going to be 1 here. Oh, thank goodness. I thought this was never going to end. That means that fib of 1 is 1. Then I got to evaluate fib of 0. When I do fib of 0, n is equal to 0. It is equal to 0. So fib of 0, since n is equal to 0, it's just going to return 0. 1 plus 0 is 1. That tells me fib of 2 is 1. Oh, baby. Progress is being made. Now, if you were really, really smart, you could just say, well, at this point, I know what fib of 1 is. Fib of 1 is 1. I know what fib of 2 is. Fib of 2 is 1. And you could just start crossing them off like that. But I don't do these things because they are easy. We do them because they are hard. I'm going to keep going and actually do the whole recursive call how the computer would do it. So then next, it would go over here. It's got to finish what fib of 1 is. Let's see. What's fib of 1? Fib of 1. When n is equal to 1, it just returns 1. Oh, baby. So this is just 1. That tells me that fib of 3 is 1 plus 1, which is 2. And so that comes down here. Fib of 3 is 2. I finished the left side. Then I got to do it right. All right, what's fib of 2? Let's see here. Fib of 2, 2 is not equal to 0, 2 is not equal to 1, so I got to do fib of 2 minus 1, which is 1, plus fib of 2 minus 2, which is 0. And again, you guys are smart. You could just go, hey, well, I know what fib of 1 and fib of 0 are. I figured it out up here. But that's not what the computer would do. The computer doesn't know that it already did it. It has to do it again. So it would go through and go, oh, excuse me, wrong color. It would go, what's fib of 1? I got to figure that out. Fib of 1. Let's find out. Fib of 1 is 1 is not equal to 0. 1 is equal to 1. When n is 1, I'm just going to return 1 here. So this guy is 1. Then I got to figure out what fib of 0. Get out. I got to figure out what fib of 0 is. 0 is equal to 0, so that would return 0 there. 1 plus 0 is 1. So I know fib of 2 is 1. 2 plus 1 is 3. And oh, baby!
Hey, we got it.
Oh,
We got it! Is it right? Let's find out. We found out the fourth Fibonacci number is 3. 0, 1, 2, 3, 4. Too easy. Hey, why don't you give me a challenge? Oh, sorry, my arm hurts. All right. So this one looks a little crazy compared to the factorial because each one had 2 calls going on. Fib of 4 called fib of 3 and fib of 2. Fib of 3 called fib of 2 and fib of 1. Fib of 2 called fib of 1 and fib of 0. And then that zipped back up. This zipped back up. And then we had to do the right side. Fib of 2 called fib of 1 and fib of 0. We know those. That zip back up. These zip back up. And we get fib of 4 is equal to 3.
Yeah, it is.
Yeah. I don't think these are hard. It's like, it's more of a visual, if you're a visual like type of person, I think these are great. I think they're really, really fun to do if you're a visual type of person. It's just kind of I mean, all you're doing is addition, really. But then you got to figure out who's calling what and where it's going and all of that jazz. Does anybody have a question about this one? Yes.
It was made to like calculate the Fibonacci numbers like thousands of places.
Yeah.
Wouldn't it make more sense to instead of doing all those steps, you think like maybe an array of the first like 10, so then it doesn't have to
Trevor is totally right. Some problems make sense to do recursively. Most of the time, like 99% of the time, it makes more sense to do it iteratively, which means like using a loop, using stuff like that. But this does pop up every once in a while, and in some languages, it's like the only way to do things. So Trevor's totally right. It probably would make more sense to do Fibonacci with a loop, but you might see it on a test, and it pops up in other programming languages and definitely in your computer science classes. So 99% of the time, probably a loop would be the best way to go, like Trevor was saying. But recursion does pop up every once in a while, and more importantly, the College Board says we have to know it. So yeah, Max.
What would happen if you tried to do a recursion with like static
A void method. Well, you could have recursion where it just prints, as like the base case is printing, and so instead of getting a final result at the very end, you'd probably have just a bunch of output on the screen. So you could technically have a void method, and these actually are static. I just made them static so I didn't have to create like an object, a Fibonacci object or something like that. I could just, like from the main method in Jelly It here, I made them static so that I could just, here, let's say instead of doing fact of 10, if I wanted to do fib of 4, like we just did together, let's see what Jelly It does. Since it's static, I can just say this without creating an object, right? So Jelly It doing fib of 4, let's see what that looks like. Speed. I've got the need for speed. Fib of 3 equals 0, okay. Is 3, 1, no, it's okay. It's called fib of 2. Oh, baby. Look at it go. She's purring. I know, Jelly It's just bonkers. It's got like a stage and God knows what else. I'm like 100% mesmerized. I don't know, I think we did it faster. I could say that, but I'd be lying. Ours kind of look like this, but I think Jelly, you just have to reverse the tree. You'd have to go bottom to top instead of top to bottom. Didn't ours look like this?
Sure.
Yeah, come on. Come on. Ours was just top to bottom instead of, or bottom to top instead of top to bottom. This isn't really how the stack looks in computer. Okay. What you now have in front of you, or you should, did everybody get a packet?
Yep.
Okay. You should have this packet in front of you. Sorry, it looks like it was photocopied once in 1977 and then passed down. That's just not true. It's just a bad copy. So what you're doing here on the first page, all you're doing is underlining the recursive call and then describing each base case and what's returned. So in this first one, thank you, Annie. In this first one, for example, here, Max, here's one that's void and just prints. So in this first one, it says underline the recursive, so underline the call to the same method. So since the method's called mystery 1, here's the recursive call right there. And then it says describe the base case. In other words, when does it stop? Well, I would say there's not a clear base case because this one's void. I would say the base case is when it doesn't call itself. So in this case, it's not going to call itself when x divided by 10 is not equal to 0. How would you explain that in English?
It's greater than 10 or greater than equal to 10.
Base case, yeah, x is, right? Yeah, greater than 10, right?
Or equal.
Oh yeah, or equal to. Because if x is 10, 10 divided by 10 is... Wait. It's less than 10. Sorry. The base case here is when x is less than 10. Because when x is 9, 9 divided by 10 is going to be 0, so it won't call itself. Does that kind of make sense? Now, what is returned for each base case? Essentially, in this base case, there's nothing returned because it's void. Nothing returned because void. However, it would be printing out x mod 10 and x mod 10. So that's what you would kind of do for the first one. All you're doing is underlining where it's calling itself, then explaining what the base case is and what's returned when you hit the base case. Let's do one more together because this one's kind of weird. Okay, on the next page, this method's called Mystery 2. So here is the recursive call. Mystery 2. That's where it calls itself inside of the method. So that's my recursive call. I've underlined it. Then I have to describe what the base case is. Essentially, when does it not call itself? When does the recursion stop? Yeah, when n is 0. And what does it return in that case? Returns 1. So that's what you're doing on this first sheet here, is just recognizing where the recursion is and identifying the base case. Again, what's the base case? It's where it stops calling itself. You don't even have to do any tracing. That's all you're doing on this first worksheet. That being said, when you finish the first one, the second one you are actually doing tracing like we did together on the worksheet. Do your best. It doesn't have to be perfect, but they do have an example that kind of uses the box method there that I was trying to teach you. And so in the second part, it says start evaluating. So on the second sheet, it says like evaluate factorial of 5. And you'll use the method that they give you and actually evaluate it, hopefully using the box method, something like that. And there's a couple on the back as well. So you have the last 10 minutes to kind of work on this here. That is your homework. Hopefully people are now signed up for the AP test and all that stuff. And so this is your homework, is finishing this packet, and we'll check it tomorrow. Any questions? All right. If you're really struggling with tracing, I did put up a couple links. I put up the link to Jelly It if you'd like to download it at home or on your computer. There's also this Java tutor that you can do tracing with as well. That's just in the web base, so you could do it on your phone. You could do it on a Chromebook. And I put up a video of this teacher doing some Java tracing as well with recursive methods. So any of that stuff should help you if you're stuck, struggling, and obviously I'll put up the video of us. Okie dokie.